Little Tigga, little Tigga, little Tigga. Today, I'll be helping you with your math. As you can see, I'm rocking the Lindsay Takamura merchandise, so make sure you guys go ahead and like, share, subscribe, turn on that bell for notifications. I'm gonna shut the fuck up now. All right, let us do these problems. All right. Let's do question number 1. A particle moves along a horizontal line so that's position at any time, blah, 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 blah. Find the instantaneous velocity at time t equals blah, 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 blah. Okay. 1. A. We're going to do it like that, okay? Find the instantaneous velocity. Okay. So we're given the position function. So we need to find the velocity function. What is the velocity function? The velocity function is the derivative of the position function. So if we want to try to find the instantaneous velocity, we have to derive, that's right, derive the position function, okay? So if we're going to derive s of t, that's going to give us 3t squared. Oh, wait, no, that's freaking what? Yeah, 3t squared minus 24t plus 36, all right? And we're going to evaluate this at t equals 3. So at t equals 3, that gives us, what the fuck is going on? Okay. That gives us, this is an arrow, by the way, gonna give us, holy shit, -9, I think. Yeah, -9 meters per second, because we gotta include units, you know. B, when is the particle at rest? Okay, so when we're asked about questions about when a particle is at rest, or moving right, or moving left, or the direction and everything, we wanna look at the velocity, because we know that when velocity is positive, that means it's moving to the right. And when velocity is negative, it's moving to the left. And when velocity is 0, it's at rest, okay? So we already have the velocity function, all right? So whenever the output of this velocity function is positive, then it's moving to the right, and so on, so on, so on. How can we find out when it's moving to the right and when it's moving to the left? Well, we can first set it to 0 to know when it's at rest. And then we can do that number line thing where you're drawing the sign chart and everything, okay? I'll just explain it, okay? So, all right, we're going to set this equal to 0. So we're going to say 3t squared minus 24t plus 36 equals 0, okay? And we can divide both sides by 3, and we get t squared minus 8t plus 12 equals 0. And this factors out to t minus 2 times t minus 6 equals 0. If you don't know how to factor, just let me know, okay? So this equals 0. So if t minus 2 or t minus 6, if either of them are 0, then that gives 0, right? So when t minus 2 equals 0, then we have t equals 2. And when t minus 6 equals 0, we have t equals 6, okay? So now we can draw our sign chart, 2 and 6, okay? So we know at these points, think of it kind of like critical points. At these points, it's at rest, okay? And now we got to choose values in between these and outside of them to see whether it's moving right or left. So let's choose to the left, less than 2. Let's choose 0, for example, okay? At 0, what is the velocity? The velocity is going to be 0 minus 0 plus 36, so it's going to be positive, okay? And then from 2 to 6, let's choose a random number like 3, okay? If we already figured out what it is at t equals 3 from part A, and that's -9, so this is negative. And then after 6, we'll just choose like an easy one, like 10, okay? And this is going to be 3 times 100, which equals 300 minus 240. Oh my days, I can't do math. This is still positive. Okay, it's positive, it's positive, it's positive, okay? So now we know that at rest, at t equals 2 and t equals 6, okay? Right from t is less than 2 and t is greater than 6, and it's going to the left when it's in between 2 and 6. Like that, okay? B is done. C, displacement after first 8 seconds. Okay, displacement, when we're finding displacement, we're just taking the end position minus the beginning position of the interval, okay? So after the first 8 seconds, so the interval of time for the first 8 seconds is from 0 to 8, right? So we're gonna find the position at 8 and subtract that by the position at 0, okay? So position is s, because that's what the function name is, I guess, at 8 minus s of 0, all right? I'm not going to do all the math, okay? But it is going to be 32, okay? Pretty simple, okay? We're going to move on to D. Total distance. Okay, distance and displacement are different. Displacement is just the end minus the beginning of the interval. Distance, you have to look at the times it changes direction, because if it's moving to the right and then it moves to the left, let's just say it moves to the right 2 and it moves back 2, moves to the left 2, right? The total displacement is 0 because the end is at 0 and the beginning is at 0. But the distance, right, you have to include every time it changes direction, right? So it goes 2 and then 2. So the total distance is 4, even though the displacement is 0, okay? So when does it change direction? Well, we just figured that out in part B, and that's at 2 and 6, because at 2 it goes from right to left, and at 6 it goes from left to right, okay? So we're going to find s of 2 minus s of 0, okay, because that's the first direction it's going, and then we have to add that to s of 6 minus s of 2, because that's the next direction, which is going to the left, and then we have to add s of 8, because that's the time interval, because we're trying to find the first 8 seconds, minus s of 6, okay? So basically, we're trying to find the total distance traveled for each time it switches direction. So from 0 to 2 is the first direction going right, and then at 2 to 6 it goes left, and then from 6 to 8 it goes right again. Okay, so we have to calculate the distance from 0 to 2, the distance from 2 to 6, and the difference from 6 to 8, and we just do that with this here zone. Okay, and this is going to give you. Also, by the way, okay, we're going to take the absolute values of all of these, okay? Because when it's moving to the left, like between 2 and 6, right, it's going to give you a negative value, all right? But even though it's moving to the left, -2, technically it's -2, right? The total distance is still a +2 being traveled, okay? It's like, even if I'm driving to the left, I'm still like going 2, okay? So we're going to take the absolute value of all of these, and that gives us... Holy shit, I'm retarded. I think it's 96 meters, okay? Acceleration. Okay, this is very easy. Acceleration is the derivative of velocity. So we're gonna, acceleration equals the derivative of the velocity, which equals, holy shit. Where's my velocity fucker? Oh, here. This is my velocity fucker, okay? It's gonna be 6t minus 24, all right? So, what is it at t equals 3? So at t equals 3, acceleration of 3 is equal to 6 times 3 minus 24, which equals a -6. All right, so don't forget the units. It's acceleration is meters per second squared. All right, F, graphs. Fuck no, we are not doing graphs, bro. You can do that by yourself. I'm not drawing no graphs, okay? G, speeding up versus slowing down. All right. Now here's the thing you gotta know, okay? Speeding up versus slowing down, okay? If I'm going this direction, okay, let's just say this direction is positive. If I'm going this direction and my acceleration is positive, then I'm gonna be speeding up, right? It's like driving a car, okay? And if my acceleration is negative and I'm going this direction, then the acceleration is like putting the brakes on the car. You're gonna slow down, right? So we can kind of think of it as, oh my gosh, if the acceleration is positive, then we're speeding up. If it's negative, we're slowing down. Fuck no, don't think of it like that. You're gonna get fucked in the ass, okay? Because look, when we're going this way, all right, our velocity is negative because we're going to the left now. If our acceleration is negative, we are speeding up in the negative direction. We are still speeding up, okay? Even though acceleration is negative, that does not mean we're slowing down. We are still speeding up. And if we're going this way and our acceleration is positive, then we're slowing down, okay? So what does that mean, okay? It means that when velocity and acceleration are in the same direction, then we're speeding up, okay? If they're in the opposite directions, then we're slowing down, okay? So we already have this thing, okay? Just that I circled that little sign chart over there, okay? For velocity, so we know when velocity is positive and negative. We gotta do the same thing to know when acceleration is positive and negative, all right? So to know when acceleration is positive and negative, we must set it equal to 0 to find when it's 0, and then do the same thing as we did with this, okay? So we're gonna say 6t minus 24 equals 0, and that gives us t equals 1. So we're gonna draw a little thing at 1, all right? And above 1, acceleration is gonna be positive, okay? And below 1, like 0, it's gonna be negative, okay? So whenever they're the same sign, okay, then that means we're speeding up, okay? So let's say they're both positive, okay? So both positive means it's gotta be greater than 6, or greater than 6 and greater than 1. Okay, so if it's greater than 6 and greater than 1, right? What does it have to be? Greater than 6, right? Because if it's greater than 1, like it's 2, it's not greater than 6. So it has to be greater than 6. So t greater than 6, all right, is when it's speeding up. Because the reason why I'm not doing less than 2 is because how can something be less than 2 and greater than 1 at the same time? You know, not possible, okay? So that is speeding up. And then also speeding up is when they're both negative. So in between 2 and 6 and less than 1. Is that possible? Can it be between 2 and 6 and less than 1? Think about that. Hell nah, okay? So we don't gotta worry about that, okay? Now, when they are different. All right, let's say velocity is positive and acceleration is negative. So it's gotta be less than 1 and less than 2, okay? Because when it's less than 1, acceleration is negative, and when it's less than 2, velocity is negative. So if it's gotta be less than 1 and less than 2, what does it gotta be? It has to be less than 1, because if it's like 1.5, yeah, it's less than 2, but it's not less than 1, okay? So it has to be less than 1. So t less than 1, slowing down. Now, can it be, because we know velocity is also positive greater than 6, can it be greater than 6 and less than 1 at the same time? Because we want to make sure that velocity is positive and acceleration is negative. No, it cannot be, okay? So we don't have to worry about that. Now we're going to the second case where velocity is positive and acceleration is negative. Or no, when velocity is negative and acceleration is positive. So velocity is negative between 2 and 6. And acceleration is positive at above 1. So when is it between 2 and 6 and above 1? So like if I have 2 here and 6 here and above 1, right? It's got to be between 2 and 6. Okay? So 2 is less than t is less than 6 is also slowing down. Okay? Finally, we're done with problem 1. Holy, that was a long-ass problem. Problem 2. Maximum acceleration. Okay. When we're trying to find the minimum and max values of things, do you remember from, because I know winter break, you're probably washed. We want to find the critical points, okay? So when we want to find the critical points, we have to take the derivative of it, okay? We got to take the derivative of it and then set it equal to 0, and that's how we get the critical points, okay? So if we're trying to find the derivative, if we're trying to find the max and min and the critical points of acceleration, we have to take the derivative of acceleration, okay? But here we're only given velocity, meaning we have to derive twice. The first time to get the acceleration function, and the second time to get the derivative of acceleration. So let's find the acceleration first by deriving velocity. And to me, you are the star of the show still. All right, that's the acceleration function. And now we're gonna find the prime of that, the derivative of that, and that's gonna be 6t minus 6. Wait, holy shit, I'm a dumbass. I'm a dumbass. For question number 1, bro, 16 minus 24 equals 0 for part G. 16 minus 24 equals 0. T is not 1 in this situation, okay? T is 4, okay? So we actually have 4 here, okay? Meaning, I gotta speed run. Okay, this one is still true. This one is still true. T is less than 1 is slowing down. Nah, so it's gonna be less than 2 then, okay? You can think about this on your own time, but I low-key wasted time, okay? And also when it's slowing down is when it's between 4 and 6. Yeah, okay? Let me just erase this. Huh. Yeah. Okay. Wait, no. Fucking shit. I'm a dumbass. Alright. Back to question number 2. We're gonna set this one equal to 0 to find the critical points. And here we have t equals 1. Holy shit. T equals 1. Alright. T equals 1. Alright, now we can draw our little thing with 1, okay? So we're gonna plug in something less than 1 and something greater than 1. Let's say 0, okay? We're going to plug 0 into the acceleration function, not the derivative of acceleration function, the acceleration function, okay? Acceleration function at 0 is going to be positive, all right? And then at 2, let's just say 2, for example, greater than 1. 2, it's also going to be positive, okay? You know what this means? This means that this is not a maximum or a minimum at point 1. It is not, okay? So where is the maximum and the minimum? Well, joke's on you, my little tigger. There's interval, okay? I think the interval is, let me check what the interval is. I'm just freaking dumbass, bro. The interval is from 0 to 3, okay? So we have to check the points at 0 and 3 as well, okay? Because remember, when we're doing this stuff, when we're finding minimum and maximum, we also have to check the intervals, okay? So we're gonna check at 0, okay? So a of 0 is gonna be equal to 12, okay? Because that's 0 minus 0 plus 12. And a of 3 is gonna be equal to a times, what the fuck? 3 times 3 squared minus 6 times 3 plus 12 is 27 minus 18 plus 12, and that is equal to 21. Okay, so this is the largest value. So we're gonna say max is at t equals 3, okay? Which gives 21 meters per second squared. All right, 2 is done. We're on question 3. I gotta start speeding, bro, holy crap. All right, so the figure on the right is the position graph, okay? When is the particle moving to the left? Okay, this is back to the left and right stuff, okay? And what do we need to know for the left and right stuff? We need to know the velocity function, okay? And the velocity function is just the derivative of the position function. And what do you get from the derivative? You get the slope, okay? So the velocity is just gonna be the slopes of the position function, okay? So whenever it's moving to the right, that means velocity is moving to the right. And when velocity is moving to the right, whenever the particle is moving to the right, that means velocity is positive. And when velocity is positive, that means the slope is positive because velocity is a derivative, okay? So that means if the slope is positive, then it's moving to the right. If the slope is negative, it's moving to the left. If its slope is 0, that means it's still, okay? So when is the particle moving to the left, right, and still, okay? I just explained it to you, okay? Slope positive, right. Slope negative, left. Slope 0 at rest, okay? B. For each of these, find the value or explain why it does not exist. Okay, so we're just gonna find the slope at all these points because it's asking for a v, and v is velocity, okay? So velocity of 1.5 is just gonna be a slope at 1.5. The slope at 1.5 looks like it's 0, okay? The slope at 2.5 looks like it's -4. And the slope at 4 looks like it's 0 again. And the slope at 5. Oh, the slope at 5 is an interesting thing, okay? Can we find the slope at 5? We cannot. You know why? Because it's a sharp angle. It's not round and voluptuous. Like your ass, for example, okay? It is sharp and angular. More like Dylan's ass, okay? And can we differentiate Dylan's ass? Hell nah, because it's sharp, okay? You can't really calculate the slope there because it's a freaking corner, okay? So at time 5 seconds, V does not exist. So we're gonna write D and E, okay? C. We're on C now. Graph the particle's velocity. Oh my days, bro. More graphing. Okay, this one's low-key important, okay? So the velocity, you're just gonna graph all the slopes. Very easy, okay? Graph all the slopes, okay? We're gonna have 1, 2, 3, 4, 5, 6. All right, so from 0 to 1, the slope is 2. Very easy. From 1 to 2, the slope is 0. And then from 2 to 3, the slope is -4. Right? And from 3 to 5, the slope is 0. And from 5 to 6, the slope is -2 again. -2. Yeah, -2. All right, now you're like, this does not look like a fucking graph, because why is it just a bunch of choppy ass lines? You know why? It's because the graph of the position, the graph given to us, has hella angles, bruh. It's hella sharp corners. It's not voluptuous and curvy, okay? So there's lots of points here where the velocity, there's just no velocity because you can't derive the position at that point, which is why it jumps on the velocity graph, okay? That's why. Let's go to D now. Graph the particle speed. Okay, speed and velocity are the exact same thing except velocity has negative, okay? Speed is always positive, so because velocity includes direction. So -2 means it's going 2 to the left, but the speed is still 2, just normal 2. So basically when we're graphing the speed, it is the exact same thing as the velocity, except everything on the negative goes to the top, goes to the positive. So from 1, 2, 3, 4, 5, 6. Okay, so from 0 to 1, the slope is still 2. Okay, from 1 to 2, the slope is still 0. Okay, but from 2 to 3, instead of the slope being -4, it's going to be 4. Okay, and then from 3 to 5, it's going to be 0. And then from 5 to 6, instead of the slope being -2, it is going to be 2. Very, very simple, beta. Question 4. We're speeding through this down. Okay, E. Okay, well, for question 4, we're given the velocity graph, okay? Be careful with which graph you're given. This time we're given the velocity graph. In question 3, we're given the position graph. For each of v prime of 4 and v prime of 20. Okay, so v prime, derivative of velocity, acceleration, slope of the velocity graph, they're all the same thing, okay? So let's try to find v prime of 4, all right? V prime of 4. So what is the slope of the velocity graph at 4? Well, guess what? 4 is another fucking corner, bro. It's like this, another fucking corner. It's not voluptuous and curvy, meaning we cannot find the slope of it because it's a corner. So this is going to be D and E. Okay? V prime of 20, on the other hand, is in the middle of this downward slope. And that slope looks like it's -20/8, which equals -5/2. Yes. Very, very good. Very, very good. Okay? B. Let A of t be the car's acceleration at time. So A, acceleration is just derivative, or v prime. Write a piecewise defined function. Okay. Interesting thing here. Why is it a piecewise function? So if you don't know what a piecewise function is, it is basically the thing where it's like brackets and it's like, oh yeah, from this interval, this is what the function is going to be. And then from this interval, this is what the function is going to be, okay? And the reason why that is the case for this part is because when we are doing, because there's so many corners, right? Just like the previous problem, the derivative graph, because for part C and D of part C of question 3, right? It's the derivative of a graph with corners, right? Because it has corners, that derivative graph is going to look very choppy, okay? So we cannot express it with a function, with one singular like function of variables, okay? We have to use multiple, all right? So we're going to do A of t equals curly bracket, all right? So acceleration is just a slope, right? So we know from 0 to 4, so this is how you're going to write the piecewise function. From 0 to 4, right? Acceleration is going to be equal to the slope, which from 0 to 4, the slope looks like it's 5. Okay? And then from 4 to 16, the acceleration is going to be 0. And then from 16 to 24, acceleration is going to be equal to -5/2. So that is very simple. That's just what it is, okay? You're kind of just writing out what you're saying, right? C, find the average rate of change and does the mean value theorem guarantee? Okay, this is an interesting one, okay? Average rate of change, okay? We're going to say average rate of change. This is the acronym ARC, all right? Just like how my ass has got an arc, all right? Is going to be equal to function at, okay, let's just say arc over interval AB, okay, is going to be equal to the function at B minus the function at A over B minus A. So in this case, right, in this case, it's going to be, because it's asking for the average rate of change of V, and we already given the velocity graph, it's going to be V of, and the interval's from 8 to 20, so it's going to be 20 minus V of 8 over 20 minus 8. And this is equal to 10. Holy fucking shit. 10 minus 20 over 12, which equals negative 10 over 12, which equals negative 1.2. Okay. This is interesting. Very, very interesting here. Okay. Now, the second part says, does the mean value theorem guarantee a value of C? So what does the mean value theorem state? Basically, if you find the average rate of change, which in this case is negative 1.2, right? And we set that equal to the derivative of whatever we're finding the average rate of change of. And in this case, we're trying to find the average rate of change of V. So if we set negative 1.2 to the derivative of velocity graph, which is the slope, right? There's going to be a point in this interval where the slope of the line is equal to the average rate of change. So basically, oh my gosh, I just said that in like way too complex words, okay? Basically, from 8 to 20 in this interval, right? Any freaking point along this line, there's going to be somewhere on this line where the slope of that line is equal to the average rate of change, which is negative 1.2. So from 8 to 20, so the graph from 8 to 20 is looking kind of like this, right? Meaning along this, there's going to be some point at where the slope equals negative 1.2. But is that the case here, right? The slope here is 0, and the slope here is negative 5 over 2. So when is it equal to negative 1.2, right? And this is why they're trying to fucking trick you, okay? The mean value does not work. Do you know why? Do you know why the mean value does not work? It does not work because the mean value theorem is assuming that the entire thing, the entire function over that interval is differentiable. And is it differentiable in this interval? No, because at point 16, there's a corner. It's freaking sharp and angular, like Dylan's ass, and not like your ass. Yeah. So because of that, the mean value theorem does not apply. So we're gonna say MVT does not apply because function is not fully how do you spell differentiable? Differentiable. Yes. All right. We're on the last problem. Lock in. Last problem, beta. Why does this problem have 3 parts? All right. So we're given a table with t and velocity. So A says use the data to estimate the acceleration. Okay. So we can't really find the slope and derivative of velocity to find the acceleration because all we're given is a table. So what do we have to use? In this case, in these cases, right, we have to use the average rate of change. All right. And what is the interval? Because for average rate of change, we need an interval, right? What is the interval going to be? Well, it's trying to find the acceleration, to estimate the acceleration at t equals 36. So what are 2 values that we can use as intervals, that values that we know that we can use as intervals that are surrounding 36? Well, we can use t equals 32 and t equals 40, right? So we can say velocity of 40 minus velocity of 30 over 40 minus 32, sorry. 40 minus 32 is going to be our average rate of change, which is going to be 7 minus negative 4 over 8, which equals 11 over 8. So this is going to be our estimate of the acceleration, okay? Now we're moving on to B. For 0 is less than t to less than 40 must the particle change direction in any of them. Okay, so what do we have to look at when we're dealing with direction, like left, right, at rest, that kind of stuff? Velocity. And luckily we're given velocity values here, okay? So basically, anytime the velocity goes from positive to negative, it's changing direction, or from negative to positive, okay? So how many times is it changing from positive to negative here, okay? Well, it has to change once from 5 to negative 10, and it has to change once from negative 4 to 7. And here it's asking the intervals at which the particle changes direction. So the interval, well, from 5 to negative 10, that's from the seconds, that's from t equals 8 to t equals 20. So we're going to say 8 to 20 is our first interval of time where it has to change direction. And our second one is going to be from 32 to 40, because that's when it goes from negative to positive velocity. Yeah, I'm pretty sure that one's pretty easy. Let's go to C. Based on the velocity of the table, what is the smallest number of instances at which the velocity could equal -9? Okay. This is one is also very just like common sense. You can just look through it one by one of the values of the table. So for velocity, right, for the velocity row, from 3 to 5, does it have to go through -9? No, it can just go 3, 4, 5, right? From 5 to -10, does it have to go through -9? This one, yes, it does. So we're gonna put a tally mark, okay? From 5 to -10, because obviously if it's gonna go from 5 to -10, it has to pass through -9, right? And from -10 to -8, it has to pass through -9 as well. So we're gonna put another tally mark. Okay, and from -8 to -4, does it have to? No, because -9 is all over here. And -4 to 7, no. Okay, so we're just gonna say twice. Okay, 2 times. It has to equal -9 meters per second. Wow, we're basically freaking done. Look at these notes, man. Oh my days. They're pretty good. All right. That is the end of this video. Please like and subscribe and hit that bell for notifications because the great Eric Wu will be posting more for Little Tigga. Peace out.